Okay, next speaker up is Andrea. Floor is yours.
Thank you. So, as you saw here, my name is Andrea Rausa, and I've been doing this work. I'm a PhD student at Politecnico Milano, and now I'm actually graduated, and I'm a postdoc researcher. But who cares? But in this presentation here, I'm going to talk about the multi-fidelity numerical-experimental database for tailplane aerodynamics that we developed at Politecnico di Milano in the context of the European project that is called Mona Lisa. So the main problem in this case is air pollution and the impact that air traffic has on this huge problem, if I say, and the fact that the aviation emissions amount for 12% of all the CO2 emissions in the world, and this number is only going to increase in the next years as the volume of air traffic increases. So how to get rid of this problem, or is how to mitigate? We can resort to advanced in technologies, new kind of operations or kind of infrastructure. But as you can see from this graph here, the projection of such impact of these technologies projected, yeah. Siamo sì, sì. Can you read from behind, or is it? So this is a projection of the impact of these new technologies until 2050, and we can see that red line is if no action is taken, so the amount of CO2 emissions is going to increase. If we use these new technologies, then it's going to decrease a little bit, but still increasing in time. And if you want to actually have a minus sign on this trend here on this graph, we have to resort to radical technologies, so change the way we think about it, about this problem, and maybe use biofuels, but that's out of the scope of this presentation. So to assist in this problem, the Mona Lisa project has been devised by the European Union and partnership with Politecnico Milano and other institutions, where we try to develop a lower numerical method that is based as far as possible, as best as possible, on a physical phenomenon, and will match experimental and numerical results, possibly including small correction factors. So this lower numerical method is something that has to be used, for example, for optimization purposes, since the number of evaluations of a cost function is going to be large. And if you use simply RANS or other numerical methods, it's going to explode the computational time required. So to do this, 5 main subjects have been interconnected. Is a uncertainty notification and a high precision model production, which I'm not going to talk about here, but the main ones are advanced wind tunnel testing, accuracy simulations, and state-of-the-art low-fidelity solvers. So this was built, what builds the multi-fidelity numerical experimental database. So the objective of this presentation is to assess how RANS and other low to mid fidelity models predictions compare against experimental results when we want to study the aerodynamic coefficients of swept tails. In particular, of swept tails, which may have dihedral angles or also contour surface deflection. So we can see reference plane here of the tail. So we have a sweep angle, which is defined simply as the angle between the normal to the symmetry plane and the line that's connecting the quarter points along the span. Then we have the ratio between the tip chord and the root chord, which is the taper ratio. And then we have the aspect ratio. So we have lots of geometric parameters that can define the geometric plane form of this tail, and also we have the possibility of having the dihedral angle. So for the Mona Lisa project, the aim was a bit too large, maybe. So we plan to inspect the huge range of such parameters. So for dihedral angles between 0 and 45, sweep angles between -30 and 30, and so on. But in this case, I'm going to talk only about specified configuration, so the reference one, which has a daily angle of 0 degrees of angle of attack and possibly 45, a sweep angle of 30, so the tip is backwards with respect to the root. Taper ratio of 0.4, aspect ratio 5, one leading edge, so that the plane for the airfoil is symmetric, and the leading edge is the. So we could have used 3. One is short, one is medium, and one is a little bit thicker. In this case, we use the medium one, and we don't take into account rise accretion. The study for this reference platform will be made by varying the angle of attack and the control surface deflection. So the angle of attack is between -26 and 26 degrees. That's because we want to capture stall. Deflection on the control surface is between -35 and 35 degrees, whereas Mach Reynolds number are set by the experimental campaign. So the Mach number is approximately 0.15, and Reynolds number based on span of the model is 5 to the 10 times 10 to the 6 power. So again, this slide is repeated. I don't know why it's here, but again, you can see that the objective is again to compare the ransom results and low fidelity models against experimental results. We have a way of assessing, for example, the surface streamlines distribution, since we use China clay in experiments especially towards the stall, to inspect how the flow behaves on top of right on top of the tail. And we can see a kind of a good agreement, at least for this case, with 0 degrees of control surface deflection and deep stall, so 22 degrees of angle of attack. So the experimental setup is you kind of see here. We have the tail geometry, which is mounted on a moving table to simulate the angle of attack variation, and then we have the control surface deflection here that is controlled by an engine. And then we have an infrared thermocamera to inspect transition also for the angles of attack that matters. And then we can see also the dots here used for warping the images from the thermocamera. For the meshing tools, we used Pointways because it allows us to create really high quality meshes, especially for the fact that the number of parameters in this case are quite large. So we want to be able to create good quality meshes independently on the, for example, having the hydral angle or positive sweep or so on. So we use dominant elements on the surface with the refinement for the region with a high curvature, for example, so the black junction here with the main body or the leading edge. Whereas for the volume, we use the voxel approach. So we have a hex dominant refinement, which follows the angle of attack, such that we can better capture the vortex structure over the tail. Safety tool, I mean, is SU2. In particular, we leverage the compressible transition and fluid turbulence capability of SU2. So we don't use a joint and anything else. So the numerical settings are that we use the Spartan-Mars turbulence model and the Bastek-Majoglu transition models, because at the time of devising this whole project, that's only what it was in the SU2 version. So now we have Lang-Elementary transition model also coupled with SST, so more studies to come. But at the time we had Spartan-Mars and Bastek-Majoglu, so we stick with that. We stuck with that across the whole project. So we used row and master reconstruction for convective fluxes. High CFL values were achieved mostly due to also the quality of the meshes that we built, and hot start strategy when changing from an angle of attack to the other one. So we restarted from the previous angle of attack to improve convergence of our problem. So we can see here a little bit of the simulation setup for the values, so Reynolds Mach number, free stream temperature, 300 Kelvin, and FST turbulence intensity also set from the wind tunnel campaign, so it's 0.1%. For low fidelity models, we use Dust, which is open source software that has been developed at Politecnico Milano and implements various kind of low fidelity models, starting from the potential theory to vortex lattice to lifting line methods and so on. And also we included a modification of the lifting line method to take into account for the cross flow phenomena. So we So you know that the lifting line is based on 2D viscous simulations of the sections along the span. And we are able, with this correction, to make these 2D solutions as 2.5D, so somehow taking into account for the closed flow. So you can see here the results of the comparing runs and experiments just for the tail geometry with 0 degrees of the radial angle. We'll have also the slides in the appendix if you want for the 45 degrees, but we'll stick with this one for now. So here we have the CL alpha curve, the CD alpha, and the CMY. So the pitching moment coefficient could refer to the aerodynamic center of the tail. And here the different colors are the different control surface deflection, and the continuous lines are RANS results, and then the dot are the experimental results. So we can see that very good agreement has been achieved for CL alpha curves, in particular with low values of angle of attack and low values of control surface deflection. That's what we know about RANs. They're good when the flow is attached, especially as part of Mars model. As soon as we increase a little bit the angle of attack or the control surface deflection, we kind of have some separation going on. So the discrepancies increase, but they are still quite good, especially for the behavior of post-hoc behavior. So we have this kind of stagnation of the CL values for both experiments and RANS results, although not really the same, but the behavior is there. The CD also is kind of the same conclusions, so we can see that maybe it's even better with respect to the CL. So the curves are really well captured, and also the values are also quite there. So as we increase the angle of attack, as the separation enlarges over the tail, then the discrepancies also enlarge, but yeah, quite good. And then also the CMY versus alpha curve are quite good. Again, the mini discrepancies are towards the post-stall regions, but we are able also to capture some kind of nonlinearities in the post-stall region for negative angles of attack that are also visible in the experimental results. So we can see this trend here and then up again and then down again, both in numerical and experimental results. So here I'm showing some results also for the dust, so low fidelity models. In this case, we are using, I'm going to show you only the lifting line because we have too many curves, otherwise it will be impossible to follow. So we are using the lifting line with the correction for the span-wise flows. And we can see again, the trends are kind of the same. So especially for lower angle of attack, so the line with the circles is the dust, so the low fidelity model. And we can see that low angles of attack, low control surface deflection, so the green curve and the blue one are quite good results, especially for the CL. Whereas as we increase to 35 degrees of control surface deflection, we can see that discrepancies are high. The CL alpha slope is not that good, and also the CL max is very high for the lifting line because it tends to overpredict the CL. And the CD curves are actually even worse in this case. So that's the limitation, of the lifting line model. It's just we try to improve it with the 2.5D, and there is an improvement with respect to the actual lifting line, but it's not a big deal. So if we zoom in the CL alpha curves in the linear of the curve, there are linearities. So here we can see experiments in the dots, and the continuous line is the RANS. You can see that there is kind of a change slope around 0 degrees, between -2 and 2 degrees for the experiment, and between 0 and 4 degrees for the RANS. So we see in both cases this change of slope, but with different magnitude and different angles. And we explained it by looking at the surface streamlines and seeing that is actually the flap side, the control surface that is separated. So we see a -2 degrees here, where the flow is attached. Then at 0 degrees, it's kind of curving a little bit the trailing edge, and we have some separation of the trailing edge, and then here the separation increases. Eventually, the whole control surface separation is separated, and so we have this kind of dip of the CL, but then it recovers because the main lift is from the main geometry. So, and this one is still attached, increasing the angle of attack. So we also inspect the luminant to turbulent transition only for certain angles of attack, because we know that it's really important only for low angles of attack. Here we can see the experimental and results with the infrared thermocamera visualization and RANS results below. It's just a plot of the skip friction coefficient magnitude. And we can see this is the case of angles of attack of -4 degrees and -6 and -35 degrees of control surface deflection. We can see that there is a transition, which is the change in color from black to white, or more white, for experiments, which kind of goes towards the leading edge, which is on the left, decreasing the angle of attack. Whereas for RANS, using the Basque-Kumajobu model, we see that we actually don't capture this transition. So here we don't have transition, here we are fully turbulent. So we kind of miss this modeling, but again, using maybe length incremental model and SST, we can maybe we actually did improve these results here. So the whole thing is going to be has been already uploaded to the Zenodo page. So the whole numerical database and also the whole experimental database, comprising of all these pictures for transition and all the sorry with all the CL alpha curves and so on, so aerodynamic coefficients, China clay visualization, everything is going to be uploaded to the Zenodo page. And the numerical files are already there with all the config files, so the meshes, it's GNS and SU2 formats, the start file if necessary, the solution, and so on. And also there will be, it has already been created an aircraft TAC wiki page for this kind of database that will reference all the data that has been uploaded to Zenodo. So in conclusion, the question was how the RANS and low fidelity models actually manage to predict aerodynamic coefficients for the swept tails with control surface deflection. And we can see that RANS actually kind of manage, especially when separation is not really that important, but we are able to capture at least the CL max value. Maybe not the alpha stall, but the CL max is even more important, if I may say. There are also nonlinear phenomena in the linear region of the CL curve that has been really well predicted, as at least in what they represent. Whereas the lifting line method shows promising results, especially for low angles of attack and low control surface deflection. So this is really an improvement with respect to RANS in the computational costs. But then again, once we go towards where angles of attack and control surface deflection, where separation is larger, then they deviate quite a lot. And laminar to turbulent transition can be predicted, but has not been in some cases by these models, by the models that we used. But for sure, further improvements in this direction can be made with different models. So as future developments, there will be actually being done the exploration of new metal geometries. So not only 30 degrees of sweep angles, but also positive, also negative, and also lower aspect ratio wings. The use of once we have these new geometries, then we can try and simulate also those geometries with the positive and negative sweep angles and see if actually RANS not only in positive angles but also in negative can predict, can have good predictions, and we see kind of here from preliminary results that it does. Then use different transition models. So again, the long-incremental transition model has been implemented in SU2. We can see that maybe so we can ask ourselves if it improves the prediction, and it does. So we can see here the Maslow model, the experiments, and the Lantry method model. So we don't have this sawtooth pattern, but we do have transitions that we don't have here, and it's kind of the same position along the chord. And then maybe if we have enough computational power, we can try some cases with the DDS simulations, which are the next step in fidelity with respect to RANs, rather than URANs. And maybe we can, for example, try and inspect those non-linearities or the stall regions where the CL is stalling, if we can actually improve the predictions there. I want to thank, of course, the European Union for the funds for this project, for that project, and for the one that I'm working on that allowed me to be here. So if you have any questions, please feel free to ask.
All right. Thanks, Andrea. I will actually start with the question from the virtual audience. So Vladimir Jovanovic is asking, does the wing contain some geometrical twist from the root to tip?
No. So no twist. It's just flat. If you may say the mean surface of the wing of the tail, or wing, as you may say, is just flat. So no twist from root to tip.
Questions from the audience.
In one of the last slides, you show a contour of the transition with the Lantry method models.
Yeah.
You also already analyzed this, the position are matching better for that case compared to the first.
Actually, yes, the CL doesn't really change that much. We improve a little bit the CD, yes, but if you see here, CD is really at that angle is really a matter of drag counts at that point. So maybe if you run a simulation longer, then it will change a little bit the value. So it doesn't really change that much. What it changes the transition is how you reach stall. So if everything is fully turbulent, then stall is delayed. Whereas if you have transition or not, maybe then you will stall faster. Or for example, when you have a control surface deflection, if the flow is fully laminar until the junction between the control surface and the main wing, then maybe it separates there. Whereas if it's fully turbulent, then it sticks and there is no separation. So that's the main advantage of actually being able to predict transition numerically. And in these cases, for low angles of attack, the actual prediction of CD was already good enough. It improves the prediction of these regions here, the non-linearities, where the stall of the control surface deflection happens. It improves that region, and improves actually the fact that we can assess the fidelity of the transition models against experimental results, in the sense of transition line on the surface.
Other questions? If not, I have a quick one. Can you give us an idea of the speed difference between the, I think it was called dust model, and the Reynolds? We call it order of magnitude, or is it negative?
Well, it depends, because so if you use vortex lattice method or panel methods, then it's a matter of seconds, because they are potential theories and they do not require any other simulation. So you just have the grid. Or if you use the vortex lattice, you only need the mean surface. Whereas if you do the panel, then you have also the width of the object. But it's just seconds. For the lifting line instead, you need to compute RAND solutions for the 2D sections of the wave. So since it has a convergent, kind of an iterative solution, the lifting line, where it checks for each span the condition, you have to pre-compute for a large range of angles of attack and Mach numbers and Reynolds numbers, the solution for the 2D. So it's just a matter of 2D simulations, and then once you have that, you can do all the lifting lines you want for that geometry. But there is this pre-processing step that takes quite some time. It's not like running fully 3D runs and so on, because you can do multiple of that because they are just 3D simulations. But it's not. It's there and we know it, but you have to do it just once for lifting line. So in the end, once you use the optimization and so on, then lifting line is also a matter of seconds in virtual.
Then let's thank our speaker, Andrea, again.